Let's take a few minutes and talk about the tridiagonal system of equations. This is a solution method that is actually, once you dissect it down and look at what they're doing, it's exactly Gauss-Jordan, except the notation is shorter, the number of operations performed has been lessened because you build in the inherent assumptions that you have a tridiagonal matrix. First of all, a tridiagonal matrix is that shown in equation 461. General form, other than the fact that everything more than one spot away from the diagonal elements is a zero. So if you followed Gauss-Jordan, or you had your computer program follow Gauss-Jordan directly, you would end up with a whole lot of operations that are nothing but 0 divided by a number, or a number, a number divided by 0 would be a problem. But you end up handling a lot of 0 operations. So this method separates everything down into 3 distinct columns so you can bookkeep the data in a smaller amount of memory and finish the problem without as many operations. So they do 3 distinct lists. It ends up being a kind of a matrix anyway, probably 3 column and however many rows to match the number of rows in the original. One column is named B, below, D for diagonal, and A, above. B, D, A. It's a very easy way to remember which one is which. And those make up the 3 coefficients in each individual row. So you actually go through it first and just take, for example, the process your book shows is that they take the first row and divide it by itself to normalize the first element to 1. Now we've heard this story before. You take that normalized row, scale it so that it matches the coefficient B2, and subtract it from the second. Lo and behold, it puts a 0 in the second row, and you've cleaned up the first entire column now to match that of the identity matrix. You carry on performing this, going row by row by row, until you achieve upper triangular form as shown here. You can't go straight, like pure Gauss-Jordan, and put a 0 right up there at the top, doing a row operation, scaling row 2 by coefficient A prime of 1, and subtracting it from row 1, because then you would essentially pollute this third element of row 1, because with the remainder of whatever element, or the scaling of whatever element row 2 column 3 would have provided to it. So it's not pure Gauss-Jordan, because you do have to go pure upper triangular, but then you can actually use the last row, all these zeros and a 1, and then now you can scale it and step backwards to eliminate all the top elements if you wish to arrive directly at a identity equivalent matrix. So you'd have identity on the left multiplied by a vector of solutions, vector of unknowns equals a vector of solutions. You could, of course, stop at the circumstance shown here in 465 and just use the upper triangular solution method, because you know in this case that xn equals b, is that double prime? Yeah, b double prime of n. Actually makes it exceptionally easy because everything is 1 on the diagonal. So both solution methods, very simple. If you want to follow a mathematical progression, perhaps to make the notation easier to put into a piece of software that you're writing, steps 1 through 5 are held there on page 143. But really, that's all there is to tridiagonal matrix solutions. It's Gauss-Jordan simplified. And again, the big advantage is that you don't have to store all the zeros in memory. You don't have to do as many operations because you know which elements are populated and which ones are not. You've built in the assumption of tridiagonal systems inherent to the problem. These show up decently often in physical systems. If I can skip forward to one example. Yes, like a series of connected springs. Whether those be mechanical springs, whether they be electrical resistors, whether they be perhaps fluid elements or heat transfer. There are plenty of physical systems that can be represented, or at least their governing equations can be represented as tridiagonal matrices. So when presented with one of those physical realizations, you know now in a more efficient solution method.